Yeah. So I've been working in the customized parallel computing research group at Heidelberg University for a few years now, and I've been working primarily on OCL remote, which is a part of this OCL library that we are maintaining and developing specifically for offloading over a network to a more powerful device. Like, there's a lot of GPU being done nowadays on mobile image recognition, classification, whatever, especially in that machine learning space and image processing with, well, maybe OpenVX, maybe something else, but the tasks are essentially the same. And doing it on a mobile device is problematic. You don't really want to do that if you can avoid it. So sometimes you just have to get the work done. So an option might be to delegate it to some more powerful machine, which is what OCL Remote lets you do without making any actual code changes to your program. If you have written your processing in OpenCL, then you can just tell it to use the OCL Remote device instead of the local GPU device, and it will offload the work to whatever the remote device is. And if you're making use of the OpenCL functionalities, like buffer migrations between devices in the same platform, then you get automatically the most optimal migration, the optimal ways to copy, depending on where the source and destination device is located. So if it's on the same machine remote, then it will copy within that remote machine without ever touching the client device in between. And typically, if you have an application that needs to offload some work somewhere else over a network, it's very common to just write a custom server for that to handle the operations for that application. But that's not without its own downsides. You need to update the client and server implementations in lockstep, unless you are very careful with the API design, which is in this kind of ad hoc cases usually not done. And because it's set in stone, the API surface where you do the offloading split, you can't really change it on the fly. For example, if your mobile device has great battery status or is connected to a charger, you might not want to offload that much. But if it's running low on power, you might want to conserve power and offload more. Or one thing that's been recently, in the last couple of years, talked about is split inferencing for machine learning, where you don't trust the server enough to give it access to the actual input data. So you do a couple of inferencing layers on the local device before offloading. And that's something that I've been experimenting with. For example, here I have an automatically generated split configuration of ResNet 50, where it's calculated the minimum distance from the inputs and outputs under the assumption that more operations makes it more difficult to reconstruct the inputs or outputs. So there I have the split, which has a set of operations that needs to be done locally. And then in the middle, a set of operations that can be offloaded with reasonable privacy. And then the final results need to be computed again locally with the last component. And in OpenCL, if you offload with OCL Remote, you do an enqueue function call in the application. It submits the commands to the OCL backend, which sends it to the server, which then enqueues it on the local OpenCL driver. And then when it's done, it sends a notification back to the client, and the client signals that this operation is now done. Yay. And that's repeated for each OpenCL enqueue command that you do in the application. That's all nice and simple, but unfortunately, sending information over an IP network takes a bit of time and has a bit of latency every time you have to start a new message, because the routing is built so that it tries to optimize itself for the current workload. So if you're not sending anything for a while, it deprioritizes you for a bit, and then you get more latency than you would if you were just streaming consistently and so on. And also, there's often quite a lot of data that you have to send, and increasing that by sending a lot of commands is, well, you can compress them, but it's still not great. So command buffers. Pretty similar to task graphs in CUDA and SYCL, and also, I think it was called graphs in OpenVX. Has been around publicly since 2021 as a provisional extension, and then there's a bunch of additional functionality on top of it with separate extensions. And like Moritz mentioned, with the OpenCL kernels, which are compiled at runtime, so are OpenCL command buffers, which means that you can also change them at runtime, and it's reasonably cheap to just rebuild a command buffer. So they don't need to be considered set in stone in the same way as like a fixed application. As for the implementation, it's quite simple to do. Just keep a list of CL command calls, and then when replaying, just go through all the recorded commands and do a CL enqueue, matching CL enqueue call with the same arguments, basically. Kernel arguments are a bit of a fun detail there, but even and others have been, and Ben have been talking about that last year, so I won't go into that much now. And they also implemented it as a loadable layer that you can just load into any ICD compatible driver on the at runtime. So it's very nice for application support, because you don't actually have to rely on each OpenCL implementation to have command buffer support. You can use it, and if the driver that you need to run on doesn't support it, you can load it in as a separate layer on top of the driver. It might not be optimal, but for the application to run, it's still good enough. And in POCL, it was also very similar. There's the conditions for the parameters to be valid are basically identical between the command buffer and direct enqueue versions of the functions. So the code for doing that is shared for like 99% basically. And for keeping the event status and signaling to the application and other commands, there's a bunch of lifecycle management at the reference counting and resource allocation and deallocation, which also got reused for the recorded commands, more or less as it was. So even implementing it in the POCL backend was pretty straightforward. So if you use the layer or the simplest implementation of the command buffers, it doesn't really change anything for the POCL remote at runtime. It still records all the commands on the client and then replays the and enqueues all the commands on the client. So essentially, you're still in the same position as far as SYCL remote is considered. So yeah, that was easy to implement and very convenient. But for offloading over the network, we still get the latency overhead for each individual command. So we're still sad. I didn't find this. I looked for the sad emoji, but it gave me the sad build store at first, so I put that instead. So the solution for that is to handle the command buffers on the server side. Unlike the command queues, where you can just enqueue commands to be executed immediately, the command buffers have to be finalized first with CL finalized command buffer KHR, which then signals to the runtime that no commands will be added. And aside from a couple of argument changes with mutable command buffers, nothing else can change really. So that's an obvious point for doing optimizations in the command graph. And if you're really ambitious, you could also try to fuse the different kernels together to build one mega kernel, and instead of doing multiple kernel invocations, just do one. But that's not something that we currently do. And it's also a very natural point in the application for batching all the commands together and sending them to the server as one big packet, which is also much easier to compress than many individual messages, because you can build like a shared dictionary for compression that compresses the general command structure really well, instead of having a new dictionary for each message. So that way, we can also reduce the number of messages we need to send to the server to just one every time we want to launch the command buffer, and obviously one for creating it in the first place. So that's nice. It solves our problem. And that is what we have done in POCL then. So POCL actually has two command buffer implementations. One is the simple overlay implementation, which works with all of the backends in POCL. You can use it with the CPU, you can use it with the CUDA backend, you can use it with the Vulkan backend. The backend doesn't actually need to know about it. And it basically just works. And then the finalize and enqueue command buffer functions check if the backend that you're trying to submit the command buffer to or creating it on has specialized support. If it doesn't, it just doesn't tell the backend about it and pretends it's an overlay. And if the backend does support the specialized implementation, then it invokes the specialized implementation instead. And the server, of course, needs to also support the specialized implementation. So the specialized implementation for finalized command buffer takes the list of commands that it gets from the client, and on the client side, they get packed into a payload buffer, which uses the exact same format as it would be as if they were written to the network socket directly, which means we can reuse the receive logic on the server. And then on the server, we take the payload buffer and parse it using the same command stream parsing logic. But instead of enqueuing the commands, we check if the OpenCL driver that the server is running on top of supports command buffers. And if it does, then it records the command buffer in that driver. And if it doesn't, then the server just saves the in-memory representations of the commands in the same format as it was received in. And when you enqueue the command buffer, then if the server supports, if the OpenCL implementation on the server supports comment buffers, then it just enqueues the previously recorded buffer. And if not, it approximates by enqueuing the commands normally, but normally when the server enqueues a command, it would also send a notification to the client when the command is done. And with the command buffers, it bypasses that, so it doesn't send a notification for each command. And instead, when it's done enqueuing all the commands, it enqueues a marker and then notifies the client when the marker is marked as finished or signaled as finished. So to the client, it still gets the event that corresponds to when the whole buffer is finished. So with that, long story short, we get a slightly different communication flow. So instead of having each command sent to the server, executed and notified back one by one, we do the whole recording entirely in the client runtime. And once we are done and finalizing the command buffer, then we send a create command buffer message to the server. And that message has all the commands already. So the server can just record its own command buffer or not record it, depending on what's supported. And it only needs to reply with the notifications. Yeah, okay, I have received your command buffer and I have recorded it locally. And then when enqueuing, it's again just one message to the server, and the server does whatever it needs to do internally to run all the commands. And only when it's done with everything, it does notify the client again. Yeah, the commands are copied in the step where the buffer is created. So just before we go, we'll go back to that in a moment. But before that, we have a small comparison. So in yellow, we have the baseline implementation, which just sends all the commands one by one. And as expected, using the client-side command buffer overlay gets basically the same performance because it's sending the exact same messages to the server. And if we instead construct the server-side command buffer, then the runtime depends a bit on the network speed. With a gigabit Ethernet, we're looking at like 1 order of magnitude faster. But that is only for enqueuing the command buffer. So what about building the command buffer in the first place? That's not part of that performance, because the idea with command buffers is that you build them once and then execute them repeatedly, like 1,000 times. So the construction time isn't that interesting in that sense. But depending on how you use the command buffers, sometimes you might want to adjust it on the fly. Like I mentioned at the start, maybe you're running low on battery, so you want to change the splits of what you do locally and what you do on the server. Or sometimes you even just want to construct the command buffer and run it once and forget about it. So it's still a valid use case, and there might be a lot of data that has to be sent when building the command buffer if it has a lot of commands. So how does that affect the performance? So my guess was it doesn't really matter that much. Finalize itself doesn't really do anything on the client side, because all the validation has been done while recording. So the finalize just sets a flag on the command buffer. And the only real question is sending the command buffer to the server. And here again, the assumption is that sending one big buffer is more efficient than sending several small messages. And yeah, that is without compression on either of them. So I made a more detailed breakdown of the performance measurements, and you can see sending the individual commands for a short buffer is basically almost the same performance as sending a 900 command buffer. So the overhead of that, of sending the buffer, is clearly not very problematic. It's basically non-existent compared to just sending all the commands individually. And again, as one might expect, sending the individual commands has pretty much the same cost as executing the command buffer with the overlay implementation that still sends them. That still sends the commands individually. So yeah, it's a bit of a obvious in hindsight, but always nice to have concrete measured numbers to back it up. So command buffers for offloading our network are great, use them. Also very easy to recommend, because it doesn't matter if your OpenCL driver doesn't support them. You can use the ICD layer to add support to any driver. Of course, that requires OpenCL 3.0. So that is something that you still need to ask the vendors to support. Yeah, and enqueuing the command buffer is way faster than enqueuing the whole processing graph separately. So that is great, and even uploading a long command buffer is reasonably fast with modern Ethernet connections, to the point that you can basically win a lot of performance for free if you bundle even a one-shot processing pipeline into a command buffer instead of executing or enqueuing the command separately. Yeah. I'm Jan Solanti from the Customized Parallel Computing Group at Heidelberg University, and I mostly work with OpenCL. So, any questions?
Thanks for the talk. There's a multi-device command buffer extension, which I think you're using for OpenCL, but you didn't mention it explicitly in the talk. Is that the case that you're using that?
For multi-device command buffers, it always falls back to the overlay implementation currently.
Okay, but you are using that extension, and
the extension is supported. Yes, it just always falls back to the overlay if you use more than one device in one command buffer.
Nice one, thanks.
I have questions.
Ask away.
What are the devices that support acceleration for command buffers? So you talked about the remote server that has support for acceleration. Are there any other backends?
So the server basically just relies on whatever the the vendor OpenCL implementation is of the device that's installed on the server. So if you have an RTX GPU on the server, then it uses the NVIDIA OpenCL driver, which doesn't support command buffers, so it falls back to replaying the command sequence on the server locally. And if you run it, for example, which is how I tested it on the OpenCL CPU driver that supports command buffers, so it records a command buffer in the OpenCL CPU driver.
And what about the level 0 backend? Does it support command buffers?
I have not tested with that.
Okay.
So at the end, you show that potentially even using this extension even if you execute the graph only once, can be beneficial because you do like this bulk sending.
Yeah.
Do you think you can do that maybe automatically? Like, I don't know, if the user never do any mem copy, you wait until the guy flush or something like that, and then you transform internally into a bulk processing.
In theory, you can do that, yes. It's just tricky to figure out where you can do it so that it actually is beneficial to anyone. Yeah. So in practice, it's not really something that's done as far as I know.
Okay.
But it's possible, yes. The common buffer API just makes it much more ergonomic, both for the driver implementation and the application implementation, because both can agree easily on where it should happen.
So I had one more general question about remote OpenCL and its usage, because from my perspective, we're entering in a world of more heterogeneous computing. And in science, especially, we start seeing code that have inference requirements that may not be satisfied on the device they're running on. And then offloading those computation to accelerators on another machine becomes a very interesting topic. So yes. Are you pursuing those HPC approach to remote OpenCL?
That's currently not a huge focus, or hasn't been. Been more interested in getting HPC or like GPU to more real-time applications on hardware where it's not physically possible to do it in real time. But HPC is a very interesting application for it. There's just, yeah, it's an interesting application. There's a lot of surface area there that needs to be covered, and like application or domain specific knowledge that is needed about the application. So it hasn't been that much in focus, but yeah, it's something that we're definitely interested in working with.
Thank you very much, Jan.